All right, so we're going to start with the first one. You'll notice with these diagrams, each and every diagram, I've placed the object on there for you. The first one, the object is placed out here. That means the object is placed beyond F and C, so it's at the far away case. The very first light ray we're going to use is, what's the first light ray? Going to go in parallel and then out through F. And so the quickest way to do parallel is you quickly measure your object right here. I have 1 centimeter. I go down the principal axis. I measure 1 centimeter. I make a mark, and then I'm going to draw in my parallel light. If I'm not drawing it in parallel, my diagram is going to be flawed, and I don't want to draw a flawed diagram. So I draw my light ray in parallel like so, and I go until I strike the mirror, and I put an arrowhead on that light ray like that. My next light ray is going to, the second half of this light ray is the reflected portion of it. Where does the reflected light ray go? It goes out through F. So I got to take from where it hit the mirror, and I got to go out through the F. You have to make sure we actually hit the F part, and we just go out like that and put an arrowhead on like so. And so that's my first light ray. The whole point of this is to find out where our image is. Can I find my image now? Why not? Why not? Very nice, Tenny. Yes, we only have one. If you only have one, you can't find an intersection between one line and itself, right? So you need another one. So what is the next light ray we're going to use? In F. So it's that light path's reversible one. We can go the backwards route. We just did in parallel out F. So now we're going to go in F. So we take our light ray like so, and we draw it down through the F like so, and we hit there. Now again, I'm going to hit there, and I'm going to do my measurement thing. I get 4 centimeters there. I move over, and I do 4 centimeters, make a mark, and then I'm going to draw out my 4 centimeters. Parallel line. And put an arrowhead on it. So now we actually have an intersection point of our two reflected light rays, but we're going to do all the light rays possible. How many light rays are we given to work with? We're given 4 to work with. We only need 2 to get an approximation, but at any given time, if you're trying to be accurate, we're going to try all 4. So does anyone know the third light ray we want to work with? Yeah, the third light ray is the in through C one. The in through C one is quite interesting. So you go in through C like so. So you take a light ray and you draw it down through C to the mirror like that. And then we remember that any line that goes through C and strikes the mirror is actually perpendicular to the mirror at that point. That's a definition of that line segment. If it's perpendicular to the curved surface at that point, that makes it a normal. So if we wanted to measure angle I, the light ray is on the normal. Angle I is the angle between the light ray and the normal. So how many degrees is there between this light ray and the normal? There's 0 degrees between this light ray and the normal. Because there's 0 degrees between this light ray and the normal, then we can use the law of reflection and say, well, angle R, angle of reflection, must also be 0 degrees. The only place angle R could be then is back along the normal, because the only place you can have 0 degrees between the light ray and the normal is on the normal itself. So then you draw the light ray back like so, and you put an arrowhead going away and an arrowhead going toward the mirror. That one's crossing very nicely at the same point I had crossed before. Yes? Now I'm going to do my third light ray. Third light ray is the least desirable, my fourth light ray. It is the least desirable of them all because it takes a little more work. It takes the most work out of all 4, but we're still going to manage to do it. The fourth light ray is into the vertex. So from the tip of the object, we draw a light ray down to the vertex like so. So from the tip of the object, we draw down to the vertex. Once we strike the vertex, we actually have to take our protractor and measure the angle of incidence. The angle of incidence is going to be the angle between the light ray and the principal axis, because the principal axis goes through C, makes the principal axis a normal. We can measure this angle. I get 11 degrees. So I measure on this side, I'm going to measure 11 degrees. And I make a mark, and I'm going to draw my light ray in from there to my mark. And I draw my reflected light ray out and my incident light ray in with the arrowhead, like so. making sure, checking over my diagram that I have all my light rays with the arrowheads on them. I've now drawn my diagram in. And the last piece is I check where the light rays cross or appear to cross. Are these light rays crossing or appearing to cross? These light rays are actually crossing. They're actually solid lines that are crossing each other. That gives us the point where they intersect. Where they intersect is the tip of the image. So that makes this the tip of our image right there. And we have I did pretty good for a guy kind of doing this on camera and using a pen instead of a pencil. I did pretty good. That's a pretty decent, solid, accurate point where they cross. Yes? All right, so now what we're going to do is we're going to describe the image for each of these so we have this recorded, what we should have. So this first image, is it real or virtual? Real. It's real. Why is it real?
It's actually on the object's this side.
And again, I know what you're saying, Edward, but the picking sides is not a long-term solution to saying this. Is that all right, sir? Because on lenses, when the image is on the same side as the object, that actually makes it virtual. If that's okay, if I give you a little forward thinking there. But if you use the terminology, the light rays are actually crossing or the light rays only appear to cross. If you use that terminology, are they solid reflected lines or are they dashed reflected lines? That'll give you an answer every time you can take to the bank. Yes? So these light rays are solid and crossing. That makes it real. Is this image inverted or erect? It's inverted. What makes it inverted? Okay, so it's pointing down when this one is pointing up is the easiest way to look at it. The definition, remember, is does it have the same vertical orientation or opposite vertical orientation of the object? And so point it up and point it down. This one is opposite orientation, so it makes it inverted. Next piece is to measure HI. We actually go at this with a ruler and we measure HI, and we get an HI of 0.4 centimeters, which I want to make a note of. I started with a 1 centimeter object. I have a 0.4 centimeter image. That makes this smaller. Yes? And so the last part is our DI. We want to locate the DI for this. Again, you're going to measure that. You measure that from the mirror itself, and you measure 1, 2, 3, 4, 4.5, 4.6. I get 4.6 centimeters. I want you to notice that 4.6 centimeters is not the same as our distance of object. Remember with plane mirrors, we always took to the bank that DO is equal to DI. Is DO equal to DI? No, it's not. I would like to make this note in here as well, though. I'd like you to note that that places this image between C and F. That this is between C and F. This image is going to be somewhere between C and F. That's where we get our image. We're now going to go to the next diagram down here. The next diagram down here, I want you to notice that we've moved the object from farther than C to on C. I want you to pay attention to my wording as well. I'm not saying in front or behind. That terminology, again, when you get to the lenses, can be very confusing. But if you say farther away than or between C and F, this terminology really helps. Not the in front and behind, that can be very confusing. So once again, we're going to use the same kind of concept. We're going to use light ray number 1, which means we have to go in over here, parallel, in parallel, out hell. In parallel, out where? Out through F. So we got to grab there and we have to go out through F like so. And put our arrowheads on it as we draw them so we don't forget them later. The next light ray is in through F. Arrowhead. And we have to measure this here. 0.9. And we draw it out. And then the next light ray is the in through C light ray. We can't do the in through C light ray. If you drew a line from the tip of the object straight down, it would never strike the mirror. So it's a good thing we had 4 light rays to choose from. It just so happens we can't use that light ray here. The last light ray is in through the vertex. So again, we have to take that light ray from the tip of the object down to the vertex. We have to put on our protractor. We have to measure the angle. I get 9 degrees. 9 degrees. Connect from the vertex out to my 9 degrees like so. And I get a nice crossing point right there. And you? Did you get a nice crossing point right there? That puts my image right here, folks. That puts my image right there. Where am I when I'm right there? My image location right there is C. So that's actually what I want to do here for my DI. My DI is actually C. So I'm getting a general answer here rather than a specific value. That general answer is the important piece. This on C case is a very important case for concave mirrors. It is the one time when you can get the object at the exact same location as the image. DO actually equals DI here. DO is on C, DI is also C. The other thing that you'll notice is that HI equals HO at this point in time. It is the one time where it happens that the image height and the object height are also the same. The other two things I need to do is, are these light rays actually crossing or appearing to cross? These light rays are actually crossing, which makes this real. And the last thing is this image erect or inverted? It's pointing downward, the object is pointing upward. That makes it inverted. And that's what we get for the terminology we're looking for as far as the 4 descriptors in the case of the object being on C. All right, so we're moving on to diagram number 3 now. Diagram number 3 is when we place the object between C and F. So this is the between C and F case. We're going to do the same thing we've been doing right along. We're going to draw in our parallel line. I know that these objects are all the same height. They're all 1 centimeter in height, so I can do my in parallel fairly quickly because I'm already used to doing it. This in parallel light ray always goes out through F, so we take our light ray and connect it from where we last were, and we draw it out through F, like so, and that's my first light ray. My second light ray is the reverse light ray. Light paths are reversible. This light has to go from the tip of the object down through F, like so, and then that light ray has to come out parallel, so I need to measure that one. I have 2 centimeters, so I move over here and mark 2 centimeters. And I'm going to draw this out like so. Good, I'm starting to see a crossing point. I still need to do another light ray. A lot of students feel that we can't use the third light ray in this case, but that's not actually true. We can. What we're going to do is we're going to go down through, we're going to use C as the direction point. That's our goal. So we're going to take C here, and we're going to take it as our direction point, and we're going to use C as a direction. So dash, 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 and then we're going to take that light ray and we're going to send it up to the mirror like so. And then we recognize it would hit that mirror and it would come all the way back like so. And so that light ray goes in on a path from C instead of through C, and then back out through C. So that's our third light ray. And then we're going to come to our fourth light ray. Our fourth light ray is the light ray that goes in through the vertex. So we take our light ray down to the vertex like so. We take out our protractor. We measure angle I above the principal axis because the principal axis is a normal, and we get a value of 11 degrees. I measure below 11 degrees, make a mark at 11 degrees. And I take my ruler and I connect out through there. And I get a light ray going that way. So this was 11 degrees and 11 degrees, and this is I, and this is R. So I end up getting a slightly flawed one in this diagram. I'm not exactly sure where I went wrong, but I have a fairly significant crossing point. I actually see 3 out of my 4 light rays crossing here. So that's the point where I'm going to call my image, because I have 3 out of the 4 crossing there. And so that's my image right in here. And I can now describe that image. I see that the light rays are actually crossing, which makes it a what kind of image? Real. I see that this image is pointing downward, but the object is pointing upwards, which makes this inverted. I can then do my height of my image. I'd measured it to be 2 centimeters earlier, so it's still probably 2 centimeters, which actually makes it larger. The HI value is important, but I'm trying to also give you, I guess, a summary sheet here, and these terms are very important for you to have. And then DI. DI we can measure. We can take our ruler and we can measure it on here. I measure that to be 10 centimeters. DI is equal to 10 centimeters. Now, that's funny because my DO is 4.7 centimeters. My DO is equal to 4.7 centimeters, which tells me this. It tells me that the DI is not equal to DO again. It was only equal in this case up here. It also tells me that I have a location for the image, and this is what I'm going to say. I'm going to say that it is farther than C. That's my general understanding. So I'd like just to review for a second here. What we've noticed happening is we start off with an object that when the object is far away, the image ends up becoming somewhere between C and F. We move the object in onto C. As we moved it onto C, we noticed that the image actually moved out to C. So they actually meet at C. That is their meeting point. We continue to move that object inward. As we move that object inward, we notice that our image continues to move out. So they are inversely related. Do you understand that? That DO and DI are inversely related. As DO comes in, DI goes out. As DO gets smaller, DI gets larger. The other thing we can notice is that we had an HI of 0.4 centimeters, then an HI of the 1 centimeters. That's what this was. And then we have an HI of 2 centimeters. Notice HI is growing as this object gets further away. All right, we're going to move on to the fourth diagram then. The fourth diagram is the diagram where the object is placed on F. When the object is placed on F, we're still doing the 4 light rays. We do in parallel out through F, so we start off with our in parallel light ray. From the tip of the object straight in parallel, and that light ray has to go out through F. Like so. Now, the next light ray is the reverse light ray, the in through F out parallel light ray. We recognize, just like we did on the in C, we cannot go in through F because that direction is not going to take us to the mirror. So we have to ignore that one. But we can still continue with the rest. Now, a lot of students have similar troubles. Well, we can't use a C. Well, that's not true. We can do it just like we did it on the last diagram. We can make a line from C, and we can use it as our direction. We can take this line from C right here, and we can say, well, C gives me the direction to head in, and then once it hits the mirror, I know it has to go back out. I recognize my dashed lines disappear, but at least it tells the story as I'm doing it, so I'm following the physics behind that light ray. The next light ray that we're going to deal with is the into the vertex light ray. So we go into the vertex once more. From the tip of the object to the vertex like so. We get on here, we measure that. I actually didn't draw it. It isn't large enough for my protractor, and I taught you this before, but I'll review it right now. I need to extend that line so I can use my protractor on it. I don't draw it solid so it doesn't give any false impressions, but it is a construction line I can use. I go back onto here, and I can measure this to be 10, 16 degrees. So I go down here 10, 16 degrees, make a mark like so. I'm then going to connect this from the vertex to that 16 degree mark, like so, and I draw it out like that. So I have my angle I of 16 degrees, my angle R of 16 degrees. very interesting. We are looking for where the light rays cross or appear to cross. Does it look like these light rays are going to cross? No, these light rays, it doesn't matter if we go forward or backward along their paths, that these light rays are parallel. When these light rays are parallel, what we are going to do in this case is we're just going to say no image, just to make life simple. We could certainly discuss this further if you are intrigued by this concept, but it's just what we're going to use. Here we go. We're now moving to the fifth location for concave. The fifth location for concave is where we have the object between C and the between F and the vertex. Once again, I want you to pay attention to my terminology. I talk about where it is on the principal axis and whether it is between or farther away than or closer than. I do not say in front or behind, because other people's understanding of in front and behind can be very confusing. So we use that terminology. So our first light ray doesn't change. It never has, and it's not going to anytime soon. So we go in parallel like that. We take our light ray in parallel, and then we draw that light ray out through F. We're then going to take the light ray that is the reverse of that, and that is the in through F light ray. This again seems very confusing. I can't go in through F because that's away from the mirror. However, we're going to use the same technique we used with the C and say, but know what? I can use F to give me the direction. So I can go dash from F like so. I can dash a line in from F, and then I can go solid towards the mirror. And once I hit the mirror, I'm good. Notice this light ray will stay. This dash part of the light ray will stay. I don't write over it like I did on the C one. It just gets to stay there. I'm then going to determine my measurement so I can actually draw the out parallel part. So this is 1 centimeter, and again I'm counting 1 centimeter, 1.5, 1.6. So I'm going to go down the mirror a little ways, the principal axis, and I'm going to measure 1.6 and make a mark, and I'm going to connect that mark with that dot like so. And so that is my second light ray. My third light ray is the in through C, out through C light ray. I can still do that. I always have been able to. I'm always going to be able to. So there we go. I'm going to use my C as a dash point to give me the direction I need. I'm going to go solid to the mirror. Once it hits the mirror, it goes back along that path. And so that is my light ray number 3. And then I'm going to do my fourth light ray. My fourth light ray is into the vertex. This is becoming a very steep angle right in here. I can recognize right now that this angle is going to be, this line's going to be too short to measure, so I'm going to dash it back so I can use my protractor. Pull up my protractor here. And I measure my angle, 10, 20, 30. I have 37 degrees, so I need to go down below, 10, 20, 30. 37 degrees like so. Like that, angle I 37 degrees, angle R 37 degrees. And I've drawn in my 4 light rays, and I go, well, this is disappointing. These light rays aren't going to cross, are they? How would we describe these light rays that are spreading apart? What's that terminology for spreading apart? We call this diverging. All right, so those diverging light rays are going that way. The beautiful thing about diverging light rays, we kind of learned about this already with triangulation. If you take 2 points of view that are divergent points of views, when you look back from where they come from, you get a convergence point. And so if it's diverging that way, it must converge that way. So we actually need to look backwards to find the convergence point or the converging point. So what I'm going to do is take the reflected light rays and only the reflected light rays. We have to make sure it's just the reflected light rays. So my first light ray was in parallel out through F. So I'm going to take my out through F part, just the reflected part, and I'm going to dash it backwards and take it there. My next one was in through F out parallel. So this is my out part. This is the part that I need. So this is the part that I'm going to draw in. The next one was in through C, out through C. So that's this light ray in here. And I have to take that light ray and trace it backwards. Sorry, my ruler's a little slippery today. Trace that one backwards. And then the last one is my in through the vertex, out of the vertex, angle I is equal to angle R, and that one's this one right here, and I trace that one backwards. And I have to tell you, I'm super excited about this because I'm kind of going pretty all guns at my diagram here, going fast. Look how nicely those cross each other, yes? All right, now, so these light rays are telling me where the image is. The image is right there. And so I know that's the place where the tip of my image is. This is the tail of my image. And so now I'm ready to describe my image. The first thing I'm going to describe is this real or virtual? This is virtual. Can anyone tell me why it's virtual? It's virtual because these light rays aren't actually crossing, right? They're only dashed lines. It's only where they appear to cross. Part B. Part B is asking me to describe whether this is erect or inverted. Well, the object points up and the image points up. So that makes this erect. The next part is my HI. I can measure my HI, and I can measure that HI to be 1.6. I get 1.6 centimeters. But what I want to note is that makes it larger. So this is unlike the virtual image that was created with a plane mirror. This image is actually larger. And the last one is I want to measure my value for this image. I get 2.1 centimeters, and my image was actually 1.2 centimeters. So my image DI is equal to 2.1 centimeters. DO was 1.2 centimeters. What we want to mention is DO does not equal DI. And that concludes our concave mirror diagrams. We're now going to move on to the last diagram. And you say, what do you mean last diagram, Mr. Wright? You made me do 10 diagrams, and this is only diagram number 6. Absolutely. I made you do 10 diagrams, and this is only diagram number 6. And you'll notice that this is the first one that's labeled convex. Everything else was labeled concave. Why am I only making you do one convex diagram? For those of you that completed your diagrams, what can you tell me? Edward?
Similar characteristics.
They all have very similar characteristics. So do we need to have 5 more observations for this? No, I'm afraid we do not. All we need to do is do this once. But you folks had to go through that experience to see how much the placement of the object affected the image. And you found that it didn't affect it as much, right? Does the placing of the object affect the image in concave? It drastically affects it. So it was really important to test all those 5. And so now we're coming up to our 6th case. So there's actually only going to be 6 cases of mirrors that you have to understand in order to be able to move forward through the mirror section we're going to work with. And that is the 5 for concave and 1 for convex. All right, let's get this done. We're now going to go in parallel. Again, we're going to use the same terminology that techniques we used before. We used a 1 centimeter height image. We're going to draw that image in parallel like so. And then we go out through F. And I had lots of people saying, well, how am I supposed to go out through F? F is there and I can't. Well, again, it's the same technique we used earlier. We don't actually have to go through F, but we can use F as given us a guide. And we show that guide by showing the dashed line, showing that we used F to get our direction out. Next, we're going to do the second light ray. And the second light ray is just like before, in through F, out parallel. To go in through F, we use the same technique we just talked about. We're going to line up our ruler with F. We're going to go solid line from the tip of the object to the mirror. Once we hit the mirror, we're just going to switch to dashed lines to show that we are using F as our direction. That light ray goes in. We now need to go out parallel. The out parallel technique is measuring how high that is. And I have 0.5 centimeters, so I go over here and measure 0.5 centimeters and make a mark, and I'm going to draw my light ray out of there, like so. Next, my light ray that says goes in through C. I can go in through C just like I went in through F's before. I just line up with the tip of the object, and I line up with C, and I draw a solid line in to the mirror. As soon as it strikes the mirror, I change it to a dashed line to show that I went in through C, and then I remember this light ray goes away like so. So it goes in through C, out through C. And then we're going to go to our last light ray. Our last light ray is the vertex light ray. We go in to that, into the vertex. I can recognize that this is going to be too short of line. I'm going to make my line a little bit longer so I can bring up my protractor right here, measure with my protractor. and I get 10, 19 degrees. So I go down here 10, 19 degrees, make a mark, and I connect from there to there. And I get angle I is equal to 19 degrees, angle R is equal to 19 degrees, and I've drawn in my light rays. And I go, oh goody, now I should be able to find my image. But I look at my reflected light rays, all of my light rays going that way, and I notice these light rays are getting further apart. They're spreading apart. What do we call the spreading apart light rays? We call them diverging. Do diverging light rays cross? No. So this side of the mirror is diverging. Now, that means if you have diverging this way, they actually must converge on the other side. So it's converging back here. So what we must do is trace our light rays backwards, our reflected light rays backwards. So we start with the first one, which went in parallel and out through F. And we notice that we actually have the out through F traced backwards already, so we don't need to draw that line in again. We're now going to go the in through F, out parallel. Well, the out parallel is there, but it isn't drawn backwards, so we need to draw that one backwards. So I need to get onto that line, and I need to draw it dash backwards like so. My next light ray is in through C, out through C, so that's this line right here. And looking by the construction process that we've done, the reflected light ray already has a dashed line behind. And then the last one is our in vertex, out of vertex right here. That's this light ray right here. We need to trace this one backwards, so we trace that one backwards. And we get a really nice convergence point right there. That convergence point is the tip of our image. That image is going to be drawn like this, down to the principal axis with a tip pointing upwards. So we now get to describe this image. Is this image real or virtual? It's virtual. Why is it virtual? Okay, I like that I'm not using actual light rays, or the light rays aren't actually there. That's the one that I like. The behind and in front will get you in trouble over lenses, because behind and in front becomes very, very confusing there. All right, so virtual. And then part B, is this thing erect or inverted? It's erect. All right, the next thing is we want to measure the height of this image. And the height of this image, I get to be 0.5 centimeters. And what I'd like to take away from that, though, isn't the actual number in this case. I'd like to take away that this is smaller. Really important. In concave, we get a larger virtual image. Do you see that in case number 5? But in convex, we're getting a smaller virtual image. Okay? Next, we're going to measure our DI. Our DI in this case is going to be 1.5 centimeters. And our DO in this case is going to be DO is equal to 2.9 centimeters. Important to notice, DO does not equal DI. And that concludes all 6 cases that we need to understand in order to thoroughly understand concave and convex mirrors.